Right, hi and good day everyone. So we continue to our lecture, okay? So last week we have discussed about sequential circuit, okay? So just to recap lah, okay? What we have discussed, right? So we have discussed on definition of what is actually sequential circuits, okay? From here. Okay, we have discussed about age triggered or age sensitive clock signal and level sensitive clock signal. So from one clock, we can either use the age or the level of the clock to trigger a sequential circuit. For example, for the flip-flop, it will be based on the age, okay, age of the clock signal, either rising edge, we not here as R, or falling edge as F. Okay, so that's actually for flip-flop. So for latch, it actually level sensitive device or component, sequential element. Okay, so level sensitive, it can be either level zero, it's sensitive to level zero, or it's sensitive to the level number one. Okay, what it actually means by sensitive? So sensitive means that it will produce the output, okay, either on the level base or edge base, depending on the type of the sequencing element. So for flip-flop, in edge sensitive, okay, so either rising edge or falling edge, or for the latch is level sensitive, either high level or low level, depending on your encoding, right? Okay, so this is actually an ideal clock, and not the actual one. Okay? The actual one is like this one. We have what we call as kind of slope, okay, due to the what we call delays inside the wiring element in the chip. So the clock cannot be generated as the one in the left. The one in the left is actually ideal one. So we also have discussed about maybe I can sketch something. So we have discussed about the setup time and hold time. Okay. So here is actually the setup time, and this area is actually the hold time. Okay. Setup time and also hold time. We have discussed that one. All right. So we also have defined, okay, sequential circuit comprises of either flip-flops or latches. Okay, so sequential circuit may have a combinational circuit inside it, but if that circuit comprises what we call either flip-flop or latches, so the whole circuit is categorized as sequential circuits. Okay, so flip-flop or latches, so flip-flop and latches is actually two different elements. It's not the same. Okay, the difference is actually it's either age sensitive or level sensitive design. Okay, if it is age sensitive, and then it is a flip-flop. If it is level sensitive, it is a latch. So these two we call as memory element. Okay, why we call it memory element? Okay, it's able to hold data. Okay, hold data temporarily. Okay, but it's actually not as memory like RAM or ROM memory. It's actually just temporary memory, just hold for a period of time. Okay, and then it will change with different data, okay, or different token, okay, depending on the clock interval, right? Clock period. All right, so this is actually will make sure that the data, okay, the data that we are operating on, okay, using our design is not catch up with others lah. So it able to differentiate between current token, we call token. Token is actually data lah. Okay. Current token, previous token, and also next token. So that's actually the purpose of having a sequencing element, flip-flop and latches. So this actually will make sure our data stable Then we can get the correct data when we come to the end of the process of the data. All right. So what happens if we don't have this sequencing element? So that will actually introduce what we call as data catching. It will catch up with previous token. Okay, and data will not be correct. We will not get the correct data. For example, you do the multiplication, for example, in your pre-lab or lab 0. So 5, for example, multiply with 3, you get 15. 5 multiplied with 3, 15. But if you don't, design it properly, you will not get that data. You will get different data due to the different in the arrival time of the input, either from input A or B of the multiplier. Okay, so we have discussed. We will just catch up now. Okay. All right. So that's actually the positive side. So the positive side. So the negative side or the limitation of it is actually it will introduce what we call as sequencing overhead. So this is actually the limitation or disadvantage of this. So, but in terms of data, it will give the stable data. Okay, you will get the correct result. That's actually the main purpose of designs digital system or digital hardware. If you design it, you can get it back faster. Okay, but the result is not correct. It's no point design it. All right, so we have to compromise on the sequencing overhead. Right. Inside the textbook, there are lots of discussion on the sequencing overhead. You can read. Okay. So we also have discussed two types of what we call example. Okay, this is very important. If I say important, you should take note on this. Okay. So on the definition of the sequencing element, okay, this one, and to understand actually what is actually the flip-flop, latches, and then how they different, okay, and then what's actually advantage of having sequencing element and also the limitation of having a sequencing element, okay, and then the trade-off between the two, as I mentioned just now. All right, so very important. And then example of sequential circuits are FSM and pipeline. So you need to go into detail. So try to explore why it is actually FSM. I think not explore. This is actually recall back what you have learned in the previous course last semester, digital integrated circuit design, or maybe digital electronic part 2 you have learned in your I think year 2. Okay. And also pipeline is also another example of sequential circuits, right? So this is actually the illustration of the finite state machine. Okay, we have combinational logic together with the what we call as a flip-flop here, right? This is actually what we call as sequential circuits, sequential circuit, right? And here is actually a pipeline. And we have different block of combinational logic circuit, and then we have flip-flop in between, okay, to make sure that the data arrive here, okay, arrive at the end, correct data, right? Okay. So detail you can explore in the textbook, right? Very important, the two examples, FSM and also the pipeline, okay. Also example here that's explain about the pipeline, okay. We have a fiber optic cable, we have discussed this, for us to transfer multiple pulses using the same, what we call the same line of fiber optic cable means that this is an example of the fiber optic cable. So we share the same cable, but we want to transmit multiple pulses. So what we do is actually that's an example is the process of pipelining. So we transfer one after another, but not simultaneously. We transfer after a period of time. For example, at T1 we transfer as we discussed here, and then after a couple of seconds, for example, and then we transfer another pulse. So and towards the end, we will reach, we will get the pulses in orderly, okay, one after another. But we're not waiting until the first pulse finish or reach the end. We transfer one after another within the interval of time. That's actually a pipelining. So it's different between a parallel. If parallel, we need to transfer, we need to have a multiple fiber optic cable as well. So that's actually parallel. Okay, maybe you can differentiate. So for example, this is the pipeline and the what we call the fiber optic cable. Sorry, not pipeline, fiber optic cable. For example, we have two fiber optic cable, and this is we have only one. So in this concept of pipeline, the concept of pipeline, we share the same fiber optic cable, only one, but we transfer one after another after a period of time lah. Okay, after a certain amount of time, we transfer the second, also the third, and so on. But for the case of parallel, we transfer it simultaneously. Okay, so we transfer at this point, okay, and then we transfer at this point simultaneously. Okay, so the advantages of pipeline is actually we share the same resource, okay, which is the cable. And this one we need to have multiple cable. Okay, so which is not cost effective and not area effective as well. Because in digital or in electronic today's, data can be transferred less than a second. And even in micro or nanosecond, the pulses can be transmitted. So why we waste the cable, just use one and then implement the pipeline instead of transferring in using multiple cables. Okay, so that's actually the scenario for you to explain what is actually pipelining, and in comparison with the parallel. Okay, so maybe I can jot down here. Here is parallel, and here is pipeline. Okay, we have also another one what we call as truly sequential, one after another, right? So maybe I can sketch here. Different color. Okay, so we have one what we call fiber optic cable, but we transfer number one, for example, token number one or pulses number one. Okay, at time t1 or maybe number one, and then we wait that pulse to arrive at the end first until it arrives, and then we transfer the next pulse. Okay, so that's actually a truly sequential, one after another. So the best one is actually we take the middle one, which is using a pipelining concept. So this can be implemented in the digital system, as we can see here. Okay, this is actually the architecture of the pipeline. Okay, we have a clock, we have flip-flop, and we have combinational logic that implement the operation, either arithmetic operation or data transfer operation. Okay. All right. So we have discussed in detail about this one, the difference between the flip-flop and latches, and then we have discussed the output in the form of timing diagram. Okay. Right. So sequencing overhead we also have discussed. Okay, and also the design of latch and flip-flop we have discussed. So in summary, latch is actually flip-flop is actually we have two what we call back-to-back back-to-back latches, and that's why you see the diagram of the flip-flop is bigger than the diagram of latch, and also same as the behavior of the flip-flop. Okay, it will update on every rising edge of every either rising edge or falling edge of the clock. Okay, compared to latch in either high or low level of the clock. All right, so we also have discussed about the types of delays, propagation delay, contamination delay, okay, and setup and hold time. Okay, so this is actually the summary. Hope everyone can recap this one. So TPD, TCD, TPCQ, and so on. So the difference is actually you just look at the D here lah. D stand for delay lah. Okay. P stand for P, propagation. So the keyword P here propagation, C here contamination. Right. So propagation, contamination, propagation, contamination. Okay. Okay. CQ is actually clock to Q, clock to the output Q. So clock to the output Q here, delay. Right. PDQ is actually the propagation delay. Propagation delay. And setup time and hold time we also have discussed, right? So back to the exercise. So you can do this exercise on your own, as I mentioned to you, do in the 1 hour asynchronous lecture last week. Hopefully you did. Okay. And then I ask you to try to answer this. Okay. So any question on this before we proceed to the next section of the lecture, which is I think clock design. Any question on this? So maybe I explain a bit so that you understand. So this question asks you to identify critical path. Okay, identify critical path. If you read this one in your textbook, I think the question is in here it's quite long I simplify it. Okay, so it's actually explain about the what we call as example of I think Itanium processor, Itanium 2. So inside this Itanium processor, this is actually a zoom in version of the, I think this is data path and ALU. Okay, so inside the ALU here, we zoom in just one portion of the ALU. Okay, and this is actually the element inside it. Okay, we have flip-flop, and we have all of these are combinational logic, all of this. So this is actually like this one. We have flip-flop. Okay, with clock. Okay, and with input. Okay, and then we have CL, combination logic. Okay, and then the output of the CL, okay, goes back to the flip-flop. Okay, so the CL is actually this one. Okay, CL is actually this one. All of this. So now you can imagine. All right, so we see it in the form of block of flip-flop and also CL. This is FF, flip-flop. All right. So flip-flop normally operate on 1 bit signal. So normally in the actual design, we use a register. Register multiple bit. The register is actually combination of multiple flip-flop. So normally one flip-flop, 1 bit. Okay. All right. So to get what we call as the critical path, so we need to understand what is actually critical path. So you did in your lab number 1, okay, to identify the critical path. Hopefully your lab number 1, you will be able to identify the critical path and also to come up with the values or the numbers, right, in your report, and with the element of the combinational logic that involved. So when we talk about critical path, so the words critical here, I think you have understand this because we have discussed in not only this in other subject right? Critical path. So critical means that is the maximum, the longest path. Okay. Why we say critical? Because the longest path will determine the clock frequency. Okay. Because of the equation of F frequency equal to 1 over T. So T here we need to consider the longest path. Okay. To consider the longest path or the critical path, actually the longest path. If we consider the shortest path, means that our system might not be able to produce the correct result because we clock at the higher speed, beyond the capacity or the capability of our system, right? So you have done the lab number 1, and then you see that the the arrival time and also the required time, right? So you get the difference between two, and then you get the slack time. And the slack time, if it is positive, means that your system is okay, and if it is negative, your system need to be clocked at lowest clock speed. Okay, in your lab, if I'm not mistaken, you set it at 40 time unit. The t is equal to 40 nanosecond, if I'm not mistaken. Okay, we can reduce the clock to maybe, for example, half of it, 20, and then we can see whether is the slack time is positive or not. If it is positive, means that you still can clock at even higher speed of the 40 time unit. All right. So back to our discussion. To get the longest path, so we need to identify how many paths that is actually available inside the combinational logic. So just to recap, so what is actually critical path? You need to identify actually the critical path. Actually, we need to identify inside the combinational logic. Okay, combinational logic. So inside this, is related to the delay, the longest delay inside the combinational logic. All right. So the longest delay here we identify through path. Which one is the longest path inside the combinational logic? So we can see here this one. This is the first path. Okay, inside the combinational logic. And we have another path, which is this one. Maybe it's different color. Here. Okay. So in terms of number of components, so we can identify here. So this is number one, adder. Number two, component number three, and component number four, and then plus actually the delay of a wire. So this is modeled as 2 millimeter wire delay. Okay, 2 millimeter wire delay. So this is actually four component. Okay, and the second part, actually one, we use different color. So one component, one element, 2 and 3 only. So that's actually in terms of number of components involved inside the combination logic. So clearly we can see it. Actually, the path number maybe we can call this is path number 1, and then this is path number 2. Okay, path number 1 is longer than path number 2. Okay, but that's actually finalize the critical path. We need to see the delay, propagation delay. Okay, so look at this. It's different. Okay, look at the propagation delay. This is actually the propagation delay. You need to sum up all the propagation delay of the two paths, and then from there you can see the total number of amount of time, delay time. So clearly here, so adder is 550 picosecond, right? So we can maybe write here 590 picosecond. Okay, and the result mark, the second element is result mark is 60 picosecond, and then we have middle bypass mark 80 picosecond, and then we have the last one, delayed bypass mark is 70. This is actually the delay on the component. On the wiring delay, we have 2. So 2 times 200 times 100 lah. So this is actually the first delay. Right here. So 100 second. Okay. This one. See clearly. Okay, and then we have another one delay in here. 100. So as comparison with this one, early bypass. So early bypass is 110, the delay, 110 picosecond. And picosecond. Okay, and this one 100, okay, same. No, middle bypass first. So middle bypass 80 picosecond. And this one 100, okay. And then the late bypass 70. So total give less than the path number 1. So path number 1 is actually the critical path. So to get it, I think they have provided in the textbook, which is here. So the critical path involve the adder, so as we discussed just now, okay, result mark and middle bypass mark, and the last one is late bypass. That's actually the 4 component or 4 element with the 2 millimeter wire, so 100 picosecond each, and then 200 lah, and the total is 1000. That's actually the TPD. So we call back your what we call your equation to get the TC. It's actually TPD plus TPCQ. Okay, propagation from clock to Q. Propagation from your clock to Q. This is actually TPCQ. And then the setup time, okay, for the what we call the clock, okay, the setup time here. So that's actually give you the TC. So to get the TC, TPCQ given, TPD we already calculated 1000, and T setup also given. Back to the question. So TPCQ is actually 90, and T setup 62, and the total you will get, I think, 1000 plus lah. Okay. Yeah, this one. So 90 plus 1000 plus 62. And then you will get the minimum TC is 1152. That's actually the minimum. And that's why you can see from the equation here, it says that, okay, this sign. Maybe I can use, okay, this sign. So this is actually the minimum. Can be more than that. Right? So when you do a design, you should have in your mind these elements of delays, so that you can predict actually what is actually the suitable F. Okay, the suitable T lah, first suitable T, and then from there suitable F. Okay. All right. Any question before we proceed?
No, Doctor.
Okay, thank you. Thank you, Das. Okay, if no question, we go to clock design. So other topic on sequencing overhead. So minimum logic delay and time borrowing, you read on the textbook. Read it on the textbook. Right. So now we go to the clock design. So why clock is so important? So we have seen it. Clock is very, very important actually, because clock is used in a synchronous design, synchronous circuit or synchronous logic. So clock is actually being used as a reference signal, okay, reference signal to trigger the operation of in a digital circle. Okay, we need to have this clock, and that's why if you can see in your lab on multiplier or in your design topic, you can see even in a demo video. So I was already explained to you about the clock in the demo video. When you do the lab, you see the main clock source here. Okay, so the main clock source here, and then you can see a lot of you can see the spine like this one. You recall back your lab number 1. Okay, so from there it will distribute the clock to clocking elements like flip-flop and also latch. Right? So clock is actually a main reference that will trigger the operation of data in our design, and that's why it's very important. That's why we learn this in our topic or in our course, VLSI design. And then clock distribution is actually the first topic that we're going to discuss. So clock distribution, actually, how do we distribute the clock throughout the chip? So this is the chip. Okay, this is the chip. So how we make sure that the clock, okay, from the main source here, okay, and the clock at the end source, at the end here, destination, at the end destination here, the same. Okay. Theoretically, yes, but in practical, no. Okay, there must be a delay because we have to transmit the clock through wires. Okay, through wire. So wire got resistance itself, and that's why we have what we call as clock. clock skew, different in clock arrival time. Okay, so clock skew is actually about the best definition we call as different in the clock arrival time. Maybe different in clock arrival. Okay. So what is actually different in clock arrival time? So it's actually, maybe I can sketch something here. So this is T1 and this is T2. Okay. So clock at T1 will not be the same as arrival time as clock at T2. Okay. So we can show it using timing diagram lah. You can explain it or demonstrate it. So if you are asked to demonstrate something, okay, you need to use a diagram with explanation. Okay, with example or diagram or timing diagram or whatever lah. So sorry about the clock to this one. So that's actually the word meaning by the word demonstrate. You need to clearly explain with support of diagram lah. Okay, so maybe this is actually clock at clock number 1, CLK1 we call clock here, and here we call CLK2, for example lah, or clock prime lah, to make it easy. And clock, and then this is clock prime, clock 1 prime. Okay, so clock 1 here, so the clock 1 prime, it will be late, like this one. The amplitude almost similar, but the arrival time will be much different. Okay, you see the difference. So see the difference. So this is at T1, and now this is T2. So different in clock arrival time. Arrival time here, T2 compared to T1 here, different. So that's actually clock skew. All right. So we need to accept this because this is actually the actual what happened in the chip, right? So that's why we need to have a skew tolerance static circuit. Okay, skew tolerance static circuit that will accept the skew, right? Clock skew. Then we will see on the domino circuit. This is I think reading lah. You need to do reading, and then on skew tolerant domino circuit. Okay. All right. So no question, No question. I proceed. So synchronous system use a clock to keep operation in sequence. So that's actually what we already discussed last time. Okay. We use clock signal as a reference to distinguish between previous and also next token and also current token. Okay, current token. So it also will determine the speed at which the machine operates. So you also did in the lab. So the F is actually determined by 1 over T. So this is actually the T comes from the clock. So this is the clock. Okay. And from here the diagram is not good. So hopefully, okay. So you see the repetitive pattern of the clock. So this is actually the T. Okay. We can also get a clock with higher clock frequency. For example, this one repeated. Oh, not good drawing. Okay, so we can see 2 different clocks. So maybe this one T number 1, this is T number 2. So T number 1 gives F number 1, and this is F number 2. So clearly we can see here F number 1 is higher than F number 2. Okay, F number 1 is higher than F number 2 frequency because of this equation. And that means that we need to reduce the time or the clock period to get the higher frequency. So clock determine the speed. Right. So clock must be distributed to all sequencing element. Okay. So sequencing element, remember we have flip-flop and edges. So that's why we need to have a clock distribution network to distribute with less clock skew. Okay, we cannot eliminate clock skew, but we can reduce it through our design, our strategy. Okay. Clock also must be distributed to other elements like domino circuits and memories. So domino circuit is actually the circuit that use clock inside it, and also memory. Memory, of course, is clock. Okay, so this is actually what we call the scenario. So I give you time to read first before we discuss, about 2 or 3 minutes. So in the meantime, if you have any questions, so just ask me or use the chat box. So our lecture, maybe we stop at 4 today to allow you to do preparation for tomorrow test. Or if you have any question regarding the topic that to be asked tomorrow, you can also ask now, not tomorrow. Tomorrow there will be no answer. You have to answer. Right?
Sir.
Yeah.
Tomorrow masuk chapter berapa, sir?
Tomorrow we cover chapter. So I answer in English because Tapa is okay. You can ask in Malay, but I will answer in English because maybe we have international students there will not understand. So I repeat your question. Tomorrow the chapter to be asked is actually a chapter on number 1 on the VLSI design methodology. Okay, one question, and the second question on the sequential circuits. Okay. We will cover that two topic. Only 2 questions. The marks, I think 30 marks. So one question, 10 marks. So maybe 2 or 3 questions for 30 marks. We have sub question That's 2 questions. We have sub question, and that give about 30 or 40 marks.
Okay. Chapter 1 and chapter 2.
Chapter 1 and partial of chapter 2 not all because week 5 we not yet finished chapter 2. Okay, sequential circuit so into chapter 1 and also part of chapter 2 including the what we call as sequential circuit design that we discussed today and that last week. So the clock part is not included. This part, clock onward is not included. Okay. Right? Okay. So take your time to read this. Any other question can also ask or use the chat box. Okay, so hopefully by reading this, you all will understand without detailed explanation from me. Okay, but if you have questions, just let me know. Okay, so the main thing is actually should arrive. Okay, or clock element is either flip-flop or latches or what we call a memory element. Okay, in the system simultaneously, in concurrently, serentak simultaneously. So that the system share the common time reference. This is what we call as reference. Common time reference means that we use the clock as a common time reference. Okay, when to do the addition, for example, when to do the multiplication, okay, when to do the operation. So it will be based on the rising edge of the clock, for example. So during the rising edge of the clock, and then do that operation. For example, during the level 1 of the clock, do that operation, for example. So that's really depends on the sequencing element that we use lah, either latches or flip-flop. Okay, so if you use flip-flop, so either rising edge or falling edge of the clock, so that will serve as a time reference, common time reference. So these elements include latches and flip-flop and memories and dynamic gate. These four elements essentially will use the clock as a common time reference. So in practice, the arrival time differs from somewhat from one point to another. So this is actually we have defined already as a clock skew. Different in the clock arrival time. Okay, different in the clock arrival time. All right. Okay, so the central challenge in clock design, okay, clock system design is to deliver the clock to the all clock element on chip. So as we discussed, I think we have the chip here. So that's actually the challenge lah. We want to what we call transfer or transmit the clock throughout the chip. Okay, because maybe we have flip-flop here, or memories element or domino logic here, and then we have here. So to make sure that they have they get the clock at the same time. That's actually the challenge. All right. Amir, you like to say something? Mama Amir. Oh, okay, so if you have any question or no? Okay. All right. So that's actually the situation. So then we also need, as a designer, okay, as a physical designer, SI physical designer, we need to find the compromise, okay, compromise between clock skew, okay, power consumption, metal resources to use, and design effort. So design effort means that how long you will need to spend, okay, to come up with the chip, okay. So that's actually the design effort, and also the what we call the expertise lah. Okay, and metal resources to be used actually it's related to the cost, related to the delays. Okay, delays also will give a clock skew and so on, and then power consumption. These are actually the elements that you need to consider. Okay, so maybe if I ask you, not in this exam in the either other exam, actually, for example, discuss between these, okay, and then relate to your task as a VLSI physical design engineer, for example. So how do you see among clock skew, power consumption, metal resources usage, and design effort? How do we compromise this? So for example, so you need to come up with your judgment based on your understanding on this course. Right? So this is an example of not to tomorrow question maybe other question. Just an example to give you an idea of how to discuss it. Right, so clock distribution, okay, so we still have time. Okay, maybe I will stop at clock distribution. Okay, let's see clock distribution. Okay, and then we have a side, and then before clock skew, and then we stop before clock skew. So clock distribution, as I mentioned to you, how do we distribute the clock? That's actually the question in the mind when we talk about clock distribution. Okay, so on a small chip, the clock distribution network is just a wire. So as I mentioned, we use wire to what we call to send the clock throughout the chip. Okay, and possibly an inverter for clock buffer. So we use inverter inside the clock distribution network to make sure that the clock less in terms of what we call as delay inside it. Okay, so on practical chip, the RC delay, remember RC delay, R stand for resistance, C stand for capacitance. Okay, so the resistance and capacitance inside the chip. Okay, resistance, normally most of the resistance come from the wire okay, that transfer the data, the clock, all right. And C is actually is not the capacitor that we create in the chip. That this is actually what we call as capacitor that exists due to the wiring in the chip. So for example, we have two wires here, okay, and then we have a gap in between, air gap, for example, or insulator in between. So this is actually will unintentionally will create a capacitor. This type of capacitor that we call as not the actual capacitor that exists due to the conducting wire. Okay, two conducting wires. So in between, it will introduce capacitor. Okay, that we don't want in our design, but we cannot avoid this because that's actually the situation that will happen if we have two conducting wires, and in between them we have gap, either air gap or insulator gap, and then it will unintentionally create the capacitor. So this element of C and R inside the wire, that will introduce delay. Okay? Delay, and that delay is actually will degrade our performance of our system, of our design. Okay. So variation in delays cause clock to get to different element at different times. So this is actually what we have discussed as clock skew. Clock arrive at different element at different times. So for example, we have here, so for example, element number 1 and element number 2. So clock here, so will be different in terms of arrival time compared to clock at here, okay, due to the RC delays. Okay. So we can use that kind of diagram to explain in your answer if I ask you. Okay, please use diagram to explain, not only a paragraph or words. Even I didn't specifically mention that, oh, with the aid of diagram. So you don't have to, restrict yourself on just paragraph of explanation. You can use diagram to explain and support your explanation, which will give you extra mark actually. Okay, when I understand what you're trying to say, then that will give you marks. But not only the diagram with explanation. If just diagram, I can also understand please take note on that. Okay. So most chips use repeaters. Okay, repeaters to buffer the clock and equalize the delay. So this is what we call how do we reduce the clock skew to reduce only what we cannot eliminate. We cannot eliminate. We can only reduce. We cannot eliminate. Does not eliminate. Just reduce the delay. This is an example. So we have GCLK. So this is actually global clock or the main clock. And we have buffer or inverter here. This is actually to make sure that the clock arriving at this clocking element, okay, maybe, for example, we have, I can label it number 1, number 2, clocking element number 2, and clocking element number 3. For example, either flip-flop or latches or domino logic or what we call memory element, okay. So we need to have, normally they use a buffer here to make sure that the delays can be reduced, and consequently we can get the clock with less skew. Right? So skew come from different in gate and wire. So we also have delay in the gate. For example, this one is inverter gate, we also get delay. And same as wire, we also have delay. So to know detail about this, you can go back to your report of your lab number 1, okay, on the synopsis design compiler. You simplify, remember you can simplify, and then you get the gate, and then you see the timing report. From that timing report, you see the delay of the gate and also delay of the overall system. So from there, you can estimate and you can see the difference between the delay of the gate, okay, in terms of numbers, how long is the delay compared to other gate from other gate to another gate, okay. And different gate got different delay. For example, NAND gate and NOT gate got different delays. Depends on the architecture inside the gate. For example, the inverter or the buffer, normally we have PMOS and NMOS, right? It's two transistors only. And compared to NMOS, NAND gate, for example, they have different internal architecture, and that's why that gives different gate delay. Right? Compared to wire, so wire, the longer the wire, the more the delay lah. So that's actually makes sense lah. The more the wire, the longer the delay. Okay. With right buffer sizing, clock number 1. Okay, this is clock 1. Okay, clock 1 and clock 2. You can see here, and we see clock 3 here. Okay, wait. Okay, so we have clock 1, clock 2, and clock 3. Okay, so to transfer the main clock, okay, to the resources, to the blocking element 1, 2, and 3. So these are actually the module. Okay, we have resistor, and we have capacitor. Okay, this is actually a model, not actually a resistor, just a model, a wire resistance and also wire capacitance. Okay, and same as this one. So clearly you can see here the longest path is actually to travel to the number 3 lah, okay, compared to number 1 and number 2, right? So clock number 2, clock 2 and clock 3 will always see RC skew. Okay, clock number 2 and number 3 will always see R and C. See R and C element, Okay. Right. So this is actually for your information. You will see the trending, okay, on the CPU performance from higher frequency. Okay. Yes, you can look into the textbook and read in your own. So how do we reduce clock skew? Okay. So this is actually the suggestion, okay, based on the experience of the designer. Okay, careful clock distribution network design. Okay, use plenty of metal wire resources. Okay, and we analyze the clock skew. Okay, and also we choose circuit structures that insensitive to skew. That's another method. So we have 3 ways to reduce the clock skew. Okay. 3 ways to deal with the clock skew, and to reduce it, we have 2 ways here, and to deal with it, we have three ways. All right, so we stop at here. Okay, we continue cloud distribution networks next week. Okay, any question before we end this class? With regard to the lecture, or with regard to the rest, maybe after I stop recording, we can discuss. Any question with regard to the lecture? So no question, So no question. So I end the recording first.